So after today's lecture, I'll update the schedule. I think we're still gonna have time to get through most of the stuff because there was kind of a fair bit of padding. In the lecture topic schedule, where it's gonna suffer a little bit is going to be in our labs. But I think that'll be okay. I think next Tuesday, we'll just use the lab time as review and practice.
Okay.
And then, so we'll do lecture today, lecture Tuesday, review and practice next Tuesday in lab, test on Wednesday or Thursday.
Okay.
Um,
I think Taylor already spoke.
yes, I did that with her. What time did you decide? Are you doing it in the morning?
Yeah.
Okay. 10's perfect. I can make sure that they have the copy by then. Everything should be good to go. That gives you a little bit of breathing room to come ask me last minute questions before you go in there too. Cool. Then we'll be set, and it's really just the labs that are going to get shifted, which is actually okay because we have more labs and we know more lab periods than we know what to do with when we get to winter and spring. So not actually missing out on anything, and what you'll eventually find out is that all the labs wind up being really repetitive anyway. It's always
Right.
set up a reflex, let it reflux for 45 minutes, do a distillation, do a recrystallization, do a vacuum. It's a lot of the same skills you've already learned, so.
So you get faster at setting all of that stuff
Yep.
up. Okay.
Yeah.
Because I feel like we're really slow at doing that right now.
We'll get there. It's a learned skill for sure, just like with anything else.
Yeah.
All right. So this is where we left off the other day. And basically, cycloalkanes in general have some interesting steric forces on them because we basically are forcing them away from being pure tetrahedral shapes. Because if you have something that is a cyclopropane, for instance, well, these are still supposed to be tetrahedral carbons, but we're forcing two of the bonds to only be 60 degrees from each other. And so that's not going to be very stable. We don't get as much orbital overlap as we would like to have when we did that. And if we expand that outward, a cyclobutane is a little bit less strained. A cyclopentane is actually pretty stable. A cyclohexane, well, a regular hexagon would have bond angles of 120 degrees, which is too much, except for the fact that we work in 3 dimensions. So you can see if you actually put these together, you view it from the top, it looks like a regular hexagon, right? Close to it. But when you actually look at it from the side, it's because it's not flat, it actually allows that it's not actually at 120 degrees, it's actually allows it to be really close to a true tetrahedral geometry. But basically anytime you get this, anytime you have a structure that doesn't allow it to be the angle that it wants to be, that causes strain energy. And we can see that if we actually look at, we can make these less stable cycloalkanes, and then in order to figure out how stable they are, what the strain energy is, we just burn them. And look at how much energy is released when they get burned. So since they're all they're all ending as water and CO2, we have the same ending point for all of these. And so they normalize by the number of carbons, heat of combustion per CH2 group. And what we see is that we get the largest heat of combustion comes from cyclopropane, then it drops, but it's still significantly higher than our minimum. And this is one of the reasons why hexagons show up all the time in organic chemistry, is because hexagons allow us to get the proper geometries. We have the least strain energy. And notice this doesn't start at 0. So it's still, they're not that drastic of a difference as it makes it look. But when we do zoom in that area, we do see that certain ring sizes are favored.
So the more strain in energy, the more energy you get from burning it.
Correct, which means the less stable it was to begin with. Right, think about if I dropped or had a bowling ball sitting here and it fell off the table versus if I balanced the bowling ball up here and it fell off. There's a lot more energy to be gained when it's less stable. All right, so the big takeaway from this is that strain energy exists. When you cause these strained geometries, they are less stable. The actual numbers don't matter as much. And the other thing to take away from it though is just that it's not a theoretical, a purely hypothetical situation. We can actually measure this difference. So we would expect though that cyclopentane should have the lowest heat of combustion if we just looked at it in 2 dimensions. Because 108 degrees is really close to 109.5 degrees, so it seems like cyclopentane should have the lowest strain energy. But that's not what we see. Because allowing it to work in 3 dimensions allows it to allows us to get that ideal geometry and minimize some other features as well. And you can also kind of see this if you take your cyclohexane and try and make it totally flat.
Taylor's somehow is, and I don't know how, because mine immediately did this.
So it'll stay like that a little bit, but if you look at the bonds, they're not totally straight. They're a little bit bent when you do that. And if you tweak it just a little bit, it'll naturally sort of, these ones are kind of, the bonds aren't as stiff as they are sometimes. But basically you're gonna wind up with the bonds being straightest and most stable when you can form these other shapes. Because that allows us to be closer to that tetrahedral shape. And here's kind of what I was talking about with the bonds being curved. If you actually have cyclopropane, it doesn't, even with cyclopropane, you don't actually get 60 degrees. A regular triangle, it has to be 60 degrees, and it's not like 3 dimensions should be able to affect that because it's only 3 points. So, but even then, we still don't actually see true 60-degree angles, because what happens instead is that these tetrahedral orbitals kind of bend away from each other a little bit. So by bending those bonds, making what they call banana bonds, the banana bonds don't have as good of an orbital overlap. So not only are we forcing the electrons to be closer than they want to be, we're making the bonds themselves weaker as well, because you can't get as much orbital overlap. And then we also see, if you look at this Haworth projection, no, sorry, Newman projection. You look at this projection. If we actually look at it in 3D along that carbon-carbon bond, we actually are kind of forcing it to be in an eclipsed configuration by doing that, right? And we just learned last lecture that eclipse configuration is not as stable as when they can be staggered.
Yeah.
But we don't really have a choice in this case because of the way that the carbon-carbon bonds are aligned. The carbon-hydrogen bonds have to be in sort of an eclipsed configuration. So there's a lot of reasons why cyclopropane is not very stable. And it comes back to a lot of those same ideas of sterics that we would have, that we've seen before. And if we replaced one of these with, say, a methyl, we would see it be even less stable. We'd be creating additional strain energy by doing that, by adding more steric interactions that way. I did, this was actually a gift from a former student.
Oh, cute.
And I noticed that my thermos, I can get 2 mugs exactly out of this as opposed to my old periodic table one where I got 2 and change. So it suits the size of my thermos better. Thanks for noticing. So we're not gonna talk a whole lot about cyclopropane moving forward because it's so unstable. Typically, what'll happen is when you make something that's this unstable, it almost always is gonna rearrange itself really quickly. It's gonna react to do something as fast as it can. In fact, sometimes that's useful and sometimes it's not. My OChem instructor in undergrad was also a contractor for a researcher for the Navy, for the Department of Defense, because this was in San Diego. Everybody works for the Navy in San Diego. And he and his research group actually made this molecule. So 2 cyclopropanes linked by a double bond. Which made it even more strained because now this is still trying to be 60 degrees, but now it's actually trying to be, it wants to be 120 because it's an sp2 carbon. And because chemists have a sense of humor, they named it Fa2025. And they actually found, they were looking at this as a potential explosive for military applications. They found that it was too explosive. Turns out that's the thing in military applications because you really don't want your explosives to explode every time you drop your backpack.
Yeah.
So, but they were just very excited they were able to make this in the first place and that they got to name it an absurd name.
Yeah, what happened to the unambiguous names?
Yeah, that's this would have been back in the 60s and IUPAC was still taking off at that point. Actually, sorry, he was probably doing his research in the 70s. It's the same instructor that told me if you ever have the choice between getting pepper sprayed or tear gassed, take the tear gas.
Really?
No, you're right, that was backwards. Take the pepper spray. And he didn't get into how he knew this. Look how unstable that.
Yeah, that's insane.
But his only explanation is, well, my then girlfriend, now wife, was living in the dorms at UC Santa Barbara in the 60s. Was his explanation for how he knew that.
Okay.
From personal experience, take the pepper spray. And so that's actually what'll happen is basically you put 6 carbons like that in such an unstable situation. These rings and these double bonds will basically pop and it'll rearrange itself to be cyclohexene.
It's that pop and rearrangement that causes the explosion.
Because it releases a fair bit of energy when it does that, and not all of it is gonna wind up turning into something else. A lot of it's gonna wind up turning into smaller molecules, and if there's oxygen around, it gives off enough energy, it can actually start the combustion process as well.
Right.
In general, unstable molecules are trouble to work with.
Well, cause then if you just use what you had here, it would turn into like this guy. It's a double bond here.
Yeah, actually, yeah, you get cyclohexadiene.
Which seems less, not very stable either, because you don't have 3 double bonds, you have 2.
Correct. And it would actually usually rearrange because of resonance structures. It would go this way. Because if you can make those double bonds alternate, you get extra resonance structures. So this is a little bit more stable than having them over here, but still not super stable.
Yeah. My bow tie turned into, I don't know, fancy bracelet. Spaghetti thing.
Well, so one of the curses of taking organic chemistry is now you're gonna see all the bad structures that get drawn for marketing purposes and graphic design purposes. And once you start noticing those, you can't unsee that.
It's like how physics is already affecting my life. I'm like, this is the acceleration of the vehicle at this point in time.
Did they have Blaze in the Monster Machines when y'all were kids?
Huh? I don't think so.
It's a cartoon that my oldest saw. He was at the beginning of it, and now my youngest is watching it. They sing songs about acceleration.
Cute. But the songs are wrong.
They're not bad actually, but they're definitely written by engineers and not physicists.
At least I got someone with a degree, right?
Yes.
Yeah.
Trying to think exactly what the phrase was. It was something like when you go from it rhymed, but it's something from something to vroom. When you go from this to vroom, that's acceleration.
That's
cheesy song, but
Yeah.
Blaze is a monster truck, goes around and uses engineering knowledge.
Nice.
So the other day he was learning about hydraulics when he was homesick with Laura. And he's like, I don't know what hydraulics are, but the song's catchy and Blaze likes them. So
I mean, that sounds like a not too bad educational show.
yeah, not so bad. It's got nothing on storybots.
That other thing you made.
So this is just a methyl group, because we're gonna come up here in a few minutes and we're gonna take cyclohexane and we're gonna stick a methyl group on it.
Okay.
Just for the sake, and then this is just
You can.
just because we can. You can fidget with this while we talk about the other ones. This is a T-butyl group or a dimethyl ethyl group.
Dimethyl ethyl.
Yes. And then I also just have a generic halogen that I'll use as a placeholder that's big, but not
Okay.
as big as this.
So that's like your R.
Yeah, exactly. When we look at cyclobutane,
Yes.
we still don't actually get, we would expect cyclobutane, if it stayed planar, would be 90-degree bond angles, right?
Yeah.
Because it's a square. We can actually make this though and observe the bond angles, and they're actually 88 degrees. They're actually closer together than we would expect. Specifically so that we can get away from being stuck in that eclipsed configuration. Okay, because remember this eclipsed configuration?
Yeah. But we go like.
It actually winds up doing that, even though that bends the bonds more. But that allows us to not have these eclipsed configurations as much.
Hydrogens push away from each other,
Exactly.
so then it would be straight.
It's more about the hydrogens that are on the adjacent ones. Because if you look at this, if you make it flat, these two hydrogens are directly eclipsed, right? And so by tweaking it a little bit, now they can be closer to being staggered.
Okay.
So that torsional, so we actually have competing strain energy here. We have the ring strain energy, trying to get the bond overlaps, but then we also have torsional strain.
Okay.
So torsional from the same root as torque. Torque has to do with what? Spinning, rotation. So anytime you've got strain that is caused by rotation, we call that torsional strain. Fun fact, that's also where the word torso comes from.
Oh, I
Because
didn't.
your torso rotates. All right, so they call this a puckered shape. Because it's not flat like you would expect, it's kind of popped out a little bit, and that causes that 88 degrees. But if you actually look along, it's on the next slide. If you actually look along one of these carbon-carbon bonds now, and do a Newman projection of it, this hydrogen and this hydrogen are now staggered. They're not eclipsed anymore. And that's what causes it to be puckered rather than flat, is so that we can get that staggered configuration instead. It doesn't do it by much, but it's better than having them directly eclipsed. So cyclopentane. Cyclopentane, we expected to have the least strain energy, right? Because it was 108 degrees internal angle. However, if you make cyclopentane and you keep it flat, you have the same issue where everything is then eclipsed.
Okay.
So even though cyclopentane doesn't have the angle strain, or shouldn't have the angle strain, it still has the torsional strain of being eclipsed, of everything being eclipsed. If I make a cyclopentane really quick, just by pulling one of my carbons out, sure, these angles are not so bad, but everything is directly eclipsed. So it also kind of puckers. You kind of get a shape that's a little bit like 4 of them are flat and 1 sticks up.
Yeah.
And it's really more like 2 of them kind of stick up. It's a little bit less symmetrical because you kind of want everything to be staggered as much as you can. You don't want anything to be directly eclipsed. And so you get kind of this like wave.
Yeah.
We still usually draw it as 4 of them are flat and then 1 sticks up because that's a lot easier to draw when you're trying to do this in 2 dimensions. But realistically, it's not like it picks one carbon that is the one carbon that sticks up. It's kind of constantly moving which one is the one that's out of plane as it's wiggling things around. Right, so both of these are once you get above cyclobutane, these are all close to the same. You look at the difference on the y-axis, it's off by 10 kilojoules per mole is all that it's fluctuating by. So it's really not that big of a deal. But it does wind up playing a role in explaining the 3-dimensional shape of these objects. So we always want to make sure we're remembering it's not a flat pentagon, even though we always draw it that way. All right, and then these ones, 7, 8, 9, 10, 11, 12, those are all pretty much the same. Once you get bigger than 8 though, then usually things will rearrange itself. If you have cyclooctane, it can pretty easily rearrange itself to be dimethyl cyclohexane. So it winds up not really sticking that much, but the fact that this number is as low as it is on the cyclohexane is why we see hexagons and pentagons showing up more than pretty much any other shape.
So it's like, why would pentagons show up more than heptagons? Is that what you call it when they're 7 sides?
Yeah, heptagons.
That sounds wrong.
Because a heptagon is gonna just rearrange into a hexagon with a methyl.
They do tend to rearrange. And
But it's a little lower than the.
so basically, once you start getting past 6, they get really floppy. And since we do organic chemistry with an eye towards biochem and biology applications, most biological applications don't make 7-sided rings because they're not rigid enough. You want it to be rigid enough that it'll keep its shape to a certain extent so that it can fit into all these protein binding sites better.
Yes.
So having 6 sides is like the goal, right? That's kind of what they.
It's the most stable, and that's why we see it the most in biochem as well. And it's not too rigid that it has all this pent up strain energy, but it's not so floppy that it won't fit into a single binding site.
Right.
So you actually see 7 and 8-sided rings more commonly in synthetic chemistry and in drug chemistry. I want to say.
But does our body like know how to break those down? even though we don't really make them ourselves.
We make molecules that are close enough that
It's not a problem.
it's not a problem.
Okay.
As long as they've got the right functional groups attached. The reason that trans fat's basically the functional group that our enzymes would try to break down. Is the part that's not natural. There are a few seven-sided rings that show up in biochemistry naturally, and then they show up a lot in pharmaceuticals. But our bodies can break them down because they've got an OH group here or a
Yeah.
chlorine over here that allows things to kind of do its thing, the enzymes to do their thing.
It's a 12. This is
Very floppy, right?
Wait, but it's more stable than some of them.
it's more stable than 6.
Cause if you have 12, you can make this shape. That kind of starts looking like there's ways to arrange it in 3 dimensions. So that it's not totally flat. You have, it's so floppy, basically, it's gonna move itself into something that's relatively stable. Or it's gonna rearrange itself into something else.
Is it just gonna split in half and go into 6 and 6?
It won't be 6 and 6 because you still have only 1 degree of unsaturation, but it might be a 6-sided ring with a bunch of methyls hanging off there or something. So this is if you make the cyclopentane and look at it down that bond angle, you can see that we actually do get things to be pretty staggered and not eclipsed by having those 5 carbons and allowing them to move in 3 dimensions. But you can also kind of see in this drawing, this is a pretty good drawing. It's basically like the back 2. It's like the back 2 carbons and the front carbon are in the same plane, and then these ones stick the other way.
Yeah.
They both stick in the same direction, but all of this is really setting the table for cyclohexane. Because cyclohexane is the one that we use as our big sort of model that we're gonna, or a case study, if you will. Because cyclohexane is really a really good model for looking at how these interactions work with each other. All right, so cyclohexane is not gonna stay flat. It's typically going to be found in one of 2 conformers. Because if you try and make it flat, you can do that, but that's kind of like balancing that bowling ball at the top of Spooner. Sooner or later, it's gonna roll one way or the other. It's at the top of a potential energy surface. And so it's gonna roll one way or the other, and it can roll into a boat configuration where you take the 2 opposite corners and put them both upward. But you might notice that then if you do that, you still wind up with everything in the eclipsed configuration. So even then, it actually won't stay truly in a boat shape. It kind of, if you take the boat structure and kind of tweak it a little bit, you get something that's kind of like a boat structure. Yeah, like that. But the one that's more stable is the chair conformer. And so the chair conformer is the one that looks like this. And I kind of picture it like it's a little bit like a beach lounger, like where you're sitting on next to the pool. It's got the little backrest sitting up. It's got the footrest going down. Nice armrests on the side. That's what we're gonna see as our most stable state for these.
The boat flipped upside down.
That's an upside down boat.
Then what's a chair?
No, sorry, what you do is if you flip that up,
Oh, that's the way the chair looks. Okay.
you could also call it a hammock if you wanted, a hammock versus a chair. But that's non-standard, so don't expect anybody to know what you're talking about if you do that. Stick with boat and chair. And these are not names that I made up. I learned these
Right.
20 years ago too. And the nice thing about the reason that the chair is so stable is if you take the chair conformer, if you look from the footrest up towards the headrest. Everything is in pretty much an exactly staggered position. If everything is in staggered position, we minimize the torsional strain. And the fact that when it was flat, everything was 120 degrees, but everything gets a little bit closer together when we tweak it into the chair conformation. So we actually have the angle strain is almost perfect. And the torsional strain is minimized as well. If we put it back in the boat configuration though, not only do we get everything is eclipsed now.
Okay.
We also get what are called flagpole interactions. If you have your boat and you put a flag at each end of your boat, they're kind of at an angle where they're pointing towards each other.
Yeah.
And so that they're gonna constantly be pushing against each other and causing steric interactions. So we have multiple reasons why the boat is actually less ideal and why when you do take it, it doesn't actually stay like this. It kind of tweaks itself a little bit off to the side to minimize those flagpole interactions. And that's what's called a twist boat.
Twist boat.
A twist boat. Twist boat is a boat that's torqued sideways a little bit. It's exactly what you don't want to have happen if you have an actual canoe. But if you can picture taking, you two seen those pink bicycle flags for Jada around town?
No, then.
They're like 6 feet tall.
Oh, I have.
They're
not seen
really big and they're like the flags are small, but they're supposed to, they put them on these 6 foot long
Right,
poles that
but-
you're supposed to put on little kids' bikes so that
Got it.
cars can see them. Make it impossible to put the bike in the garage or like on your car or anything anymore. But if you can picture taking these big long flags and attaching them to a classic canoe shape, they're gonna point into each other, right?
Yeah.
But if you torqued the boat just a little bit, they're still gonna be pointing towards each other, but now they're offset. That's what the twist boat is doing.
Yeah.
Right, and so when we start at the chair conformation is the lowest energy form. If we take it and we take one of the ends of that chair. And we flip it up so that it's flat,
It's not a chair anymore.
it's not a chair anymore. It's a half chair. It's got the footrest, it's a shalong. That's the original pronunciation of a chase lounge. It's like those, like a fainting couch, like the ones it's a like a recliner where that's permanently in the reclined position.
Like,
Well-
yes, the ones, you remember when we used to go to high tea for my birthday and they'd have those like half couches where it's like a,
Oh, yeah.
That's- yes.
So the half chair is like, the American way of pronouncing it is a chase lounge. The British way is a shalong.
You don't need to make things all.
There's a post-punk band called Wet Leg from the UK. It had a hit song a couple years ago called Shaylong. No? Okay. Anyway, that's beside the point. That's gonna be a transition state. That's going to be an unstable state.
They're staggered.
Because it's staggered, but we're creating this strain energy by forcing it to be 100, more like 120 degrees instead of 109. So it is gonna tend to either flip back down or go into the twist chair.
Twist both.
Twist boat, sorry. Thank you. Right, so it's gonna sit there for a second and really not even really a second. It's like an instantaneous moment where it's at that transition state, and then it's gonna fall one way or the other. If it falls into the twist boat configuration, can actually go back and forth between the two states. You can have this twist boat or that twist boat. They're the same energy relative to each other. But there's another little transition state in between them where you're in the true boat configuration. Where those flagpole interactions and the eclipsed hydrogens make it less stable. Part of it is that it helps if you can keep your carbons. We choose which carbons we make the points of the boat kind of arbitrarily.
But then the other ones are all moving down. That's it. On a boat.
So think of it like a canoe. The canoe's got a point at the front and a point at the back, and then it's lower along the middle.
Yeah, so I just can't get it to boat. Like I boat it and then the bottom goes down.
Right, so it's automatically putting itself into the twist boat. Because when you put it into the true boat, it's gonna naturally try and move one way or the other. And it's not gonna be perfectly symmetrical. So you get something that looks more like this, where you kind of have the edges of your boat making an X. The rails of the boat, you could say. Yeah, there's a twist boat. If you force it into the boat from there, it's less stable. It looks symmetrical, but it's less stable. If you force the twist boat into the boat. Let's see. Yeah. So this whole process of starting in a chair conformer on one side, going through the boat, and then ending up with the other carbon down is called a chair flip.
Here.
Sounds like a WWE move. The chair flip, we actually know that it actually does that. It doesn't just stay in one conformation. Because it turns out if we attach something to one of these carbons, it's gonna make things more complicated. But we can actually measure what that does. All right, so here's your step-by-step for how do you draw boat configuration, because you can't turn in your models with your test.
Right.
So if I ask you questions about these conformations on the test, you have to be able to draw it. This is the way that that one of our textbooks recommends doing is start with a wide V, draw a line down just to the right, that ends just to the right of the bottom of the V. Turn that into a V, and you get, it takes a little practice. The way that I like to do it is you start with two parallel lines. Do this so it's on the recording too. I'll come back to these directions here in a second.
Okay.
If you start with two parallel lines that are offset just a little bit, those are your armrests for the chair.
It's not step one.
That's
That is in
on,
this
this
case.
is
He's
my
giving us a
version.
different-
Oh, okay.
Then you add a V for the footrest. Add an upside down V for the headrest.
Wait, so this should be slightly offset, the parallel lines.
Yeah, so parallel line. The front parallel line should be, I usually draw it so it's offset that direction, but it doesn't really matter.
Then you add,
V to connect, to add our footrest. An upside down V to add the headrest. The bond angles aren't exactly right, but it's close enough that anybody who's taken organic chemistry is gonna know what you're drawing. The other approach. Doing it this way, you're drawing the back armrest and the back of the headrest first. Then you draw the front of the headrest. Add your parallel line.
like your way better.
It's effectively the same thing, I just start in the middle with the two parallel lines.
I think it's faster.
I would tend to agree. I like to present multiple options though, because not everybody agrees with me on everything, unfortunately.
It's just us, so.
So you pick which way works for you, I'm gonna keep doing it my way, as long as you can recognize it. Just like drawing your hexagons, some of them are gonna get sloppy while you are getting used to learning how to do this, and that's okay too.
So can we bring these to the exhibit?
I'm gonna say yes.
Okay.
You've still gotta be able to draw it
Right,
properly.
right.
Right, so as long as you can go from here's my model and now I'm gonna draw it to turn it in. Then I don't see a problem with that. Okay,
Would you let SAS know?
yeah, I'll come down with you and, or at break, I'll go tell Micah to put that on the accommodations sheet. All right, so. Why does this chair flip wind up mattering? Well, because it turns out, even though each of these carbons has two hydrogens attached to it, the hydrogens are not identical to each other. Because if you look at a chair conformation, you can see three of these hydrogens are pointed in the same direction, upward, right? And then there's three that are pointed almost straight downward. And then there's another six that kind of point away from everything else. With those three that are all pointed in the same direction, those can push on each other and have steric interactions. But the ones that point away from everything else don't. These ones around the middle, around the belt. If you think of this, if you think of the carbons as the equator on a globe. These ones that are pointed away from everything else, away from the rest of the globe, are gonna have fewer interactions than the ones that are pointing straight up or straight down. So the way we describe those, so every carbon has two positions There's an axial or an equatorial position. Alright, so the axial position are the ones that are sticking straight up or straight down. And the equatorial ones are the ones that are pointed away from everything else. So for this model as it's drawn,
So the X is going either up or down?
the X is pretty much, so hold your model. The X is this one. So it's basically perpendicular to the plane of the carbons, to the rest of the molecule. The equatorial is the one that's pointing straight away from everything else. So as long as we have our model in front of us, that makes that kind of easier to remember what's going on, because we can kind of identify visually which ones are the axial. Right? If you don't have the model in front of you, it's a little bit trickier, but you just have to remember that every carbon is gonna be more or less tetrahedral, right? So that means that this carbon has an axial hydrogen going straight down. This one is gonna have an axial position going straight up. Straight down, straight up, straight down. Basically, the axial positions are gonna be pointed away from the other two bonds that you drew. And they're gonna alternate up versus down.
And this only applies for hydrogen's axial and.
It applies to whatever is attached to the carbon. Every carbon's tetrahedral, so two of the bonds on every carbon go to other carbons in the ring structure. The other two bonds, one is axial and one is equatorial.
So then next to each of those axials is an equatorial.
Right, and that's where being able to see these as tetrahedral carbons is really helpful. Right, because if I zoom in on this one that they have drawn already and ignore the rest of the molecule. If I just look at this carbon right here, the headrest carbon.
Yeah.
This bond and this bond are in the plane of the board.
Right.
Because, and then this bond is a wedge coming out towards us. And this bond is going away from us. So it's still a tetrahedral carbon. This is one of the reasons why I was so careful early on. So like, no, you have to put your wedges and your dashes have to be in the same general direction. And then you have two bonds that are flat. It's because being able to visualize it this way is going to allow us to see the three-dimensional shape better. Now the points are not so bad. We can do the same thing down here. This one is going to have dots going there. A wedge here. Which means these two, the axial and the equatorial, are going to be in the plane of the board. If we zoom in on this front carbon right here, from this carbon's point of view, its back bond is going to another carbon. This carbon's in the plane. So where are the other two bonds attached to that carbon? One's gotta be coming out, and where is it pointing?
Oh,
Going
and then
down.
one is,
One's axial going down,
One's an equatorial going left, right?
pointing in the same general direction as the one that goes into the board. Right, and so that's why that's how we know that the axial position goes down here. It's because if we look at the other ones, we know that one of the bonds is in the plane right here.
Yeah.
We know that one of the carbon-carbon bonds is going into the board there. So there has to be a bond coming out, pointed kind of in the same way as the bond going in. The last spot that's left is straight down. So this would be our equatorial. And this would be our axial. Now, in this case, when we're just looking at cyclohexane, they're all hydrogens. You can see as soon as we replace a hydrogen with something bigger, we're gonna get some weird steric things happening.
Okay.
And that's where we're going.
Okay.
Let's do one more of these before we take our break. Let's say we're looking at that back carbon right there. So from the point of view of this carbon, what bonds do we know? We know the two carbon bonds, right? Are they flat or are they into the board or out of the board? From this carbon,
One of them is gonna be flat,
one of them is gonna be flat,
the one on the right.
yeah. So think about what this looks like. We're talking about this carbon right here.
So then the other one's gonna be out of the board, because the one on the right
Bingo.
goes into the board, so it needs to come back to meet its friend.
Exactly. Because it's a ring structure, we know that the other carbon-carbon bond has to be coming towards us in order to connect to the rest of the ring. So then where are the two hydrogens?
And one is going into the board.
One's,
The X one is going in, the X,
no,
no, the
equatorial
equatorial.
is going in,
good,
and then the axial is flat up.
bingo. Once you get the hang of it, once you have convinced yourself, okay, I know exactly that the axials are, I'm always gonna draw those as lines straight up or straight down. Then that actually, the fastest way from, once you're used to it, is just go through and do all of your axials. Because if you look at this one here, I can say, okay, well, I know my axial's up there. I know this axial's down. I know that axial's up, that axial's down. That axial's up. This axial is down. And then you can come in and add all the equatorials. Say, okay, well, that's an equatorial. That's an equatorial. That's an equatorial. The points are always the easiest ones to do.
Yeah.
And then it's a matter of going through and say, okay, well, now that's an equatorial. Where's the last equatorial going to go? On this carbon. How would we draw it? That's the trickiest one, because there's, yeah, kind of up in the same general direction as that carbon-carbon bond, because that carbon-carbon bond is really a wedge coming towards us.
Wait, but I thought the equatorial was a wedge. No, it's the other thing.
The equatorials are a wedge on the front.
Okay. I believe you.
Okay. you can always take this approach if you're not sure if you're doing it right. You can take the time, say, okay, from the point of view of this carbon, where is everything? I know I need my wedges and my dashes pointed in the same direction. What wedges and dashes do I know? What bonds do I know because of the shape of a hexagon?
Yeah.
Okay, so that way won't fail you if you get good at it. This way is faster once you get the hang of it.
I think looking at the 3D definitely helps.
It does, because you can kind of start to see, oh, it's just a bunch of lines and wedges and dashes, but you can kind of start to visualize the 3-dimension
Yeah.
aspect once you get used to it. All right, let's take our break.
Okay.
Let's come back at 5 after. And we're gonna see what happens when we start adding bigger things on there.
Right. I need coffee. Your curls look good today.
Thanks, I didn't do anything.
They look like
I slept in a braid.
yeah, I was gonna say you must have slept with
Well,
something.
because AJ's always like, your hair's in my face. He actually started saying, you need to wear a bonnet thing. I'm like, I have one. And he's like, you need to wear it. And I'm like, gladly, I would gladly wear my bonnet to protect my curls. But at first I didn't because I was like, you know, he's gonna think it's weird, right? Like, oh, you're flustered.
Yeah, I think he doesn't understand that we basically live here because he's only here for one class.
What class is it anyways?
It's a business class, but it's the same one Mikey's in, but it's year long, so he wanted to do it in person.
Cause Mike was doing it online.
Because Rory also doesn't do hockey anymore, so he has his days free.
What else do you do?
He works at Caliburn. That's it? Yeah. But he's a server, so he makes an absolute thing during busy season.
Doesn't Mikey?
No, but he's a busser and
Does he
refuses.
get tipped out?
I'm like, not as well. I keep telling him to be a server.
Yeah, he should.
He's
He's
cute,
cute,
he'd
he'd make little tips.
I don't have the menu memorized, and I'm like, I think you do.
AJ's like, I should not be a bartender. I'm like,
Yeah.
you should bartend at like a Magic Mike place where you don't have to wear a shirt, your abs, you get so many tips, babe. He's like,
God.
I'm not that cute. I'm like,
You're
to
so
grown
gross,
women,
Meg.
yes, you are.
You're so
Get the
gross.
tips so we can have a nice apartment.
Shut your mouth before I throw up.
I mean, society objectifies our bodies anyways, might as well make money off of it. Am I wrong?
I guess like for bartenders, it's a whole different world. That kind of is the thing that happens.
What?
Like they do get objectified.
Yeah.
You know, like no matter where it is.
I'm just being a supportive girlfriend.
Yeah, sure.
Put it on here.
Alright. So. Take a hydrogen off of your cyclohexane,
I don't like
Replace
where
it.
it's going.
replace it with a bromine.
Oh, I don't have one made up.
One of the big, doesn't have to be green, it can be the purple one.
Too late, you're both greened already. Now it looks like a chair. Oh, I forgot to tape glue. No, that has to stay. No, it doesn't.
Alright. Bromines are big. So it's gonna matter whether the bromine is in the axial or the equatorial position.
Wouldn't it would be more stable equatorial. But
There
it
you go.
has less energy that way.
Exactly, less stable, sorry, more stable and less energy mean the same thing. Two ways of saying the same thing. So let's practice drawing this though. In general, if you only have one thing attached to your cyclohexane, it's easiest to put it on the headrest or the footrest.
Okay.
That's gonna make it more clear because we know that the two our two axial and equatorial positions are planar then, they're in the plane of the board.
Yeah.
And then we don't need to worry about is it going into the board or out of the board as much.
Right.
Alright, so I'm gonna leave this one here so we can come back and reference it as we're drawing these things. So just pick one configuration and draw it. Easy enough, right? The other chair conformer is what happens when this goes through a chair flip.
Okay.
So in chair flip, you're gonna take the headrest and flip it down to be the footrest. And then take the footrest and you're gonna flip it up. So if we start by drawing the boat configuration, so we can see what happened here. We took this end and we flipped it down. What does that do to these two, axial versus equatorial? We took this and we flipped it down, the bromine was sticking straight up, right? So when we flipped it down,
Now she sticks straight down.
No. it sticks out.
Sticks out.
Look. Cause we don't just go like this.
Why not?
Because it doesn't do that. Instead, it goes like this. We are out of the pancake universe. We can no longer pancake.
Why?
Because it's against the rules.
Cause that's not what we're doing. We're actually switching, we're doing a chair flip, not just rotating it the way it is. We're finding a different conformer, not just rearranging the one that's already there.
So it goes out of the board?
So it was like this, bromine,
It was like this. Look, he's explaining it right now. We're like.
those models are perfect. That's why we built them, right?
Yeah.
When you flip that down, it goes, now it's no longer axial.
But it's still in the plane of the board.
It's still in the plane of the board, but now it's pointing away from everything else. So the red bromine and the blue hydrogen are still both in the same position relative to each other, but now the bromine sticks out and the hydrogen sticks down. So when you do a chair flip, everything's gonna flip axial and equatorial.
And then.
And then on the other side, it's just gonna
Right,
flip
it just
up,
flips
right?
up and then those stay down.
Right.
Janky one. That helps.
Does take practice, right?
Stay down. Okay.
Alright, so, and if you, it's easiest to see with the headrest and the footrest, why when you do a chair flip, the axial and equatorial flip. But these other ones do the same thing as well. If I have this set up so that the bromine is in the axial position on one of the armrest spots, watch what happens when you flip that headrest down. It goes from when you flip the headrest down, what's on that carbon also switches axial and equatorial. So when you do a chair flip, everything that was axial is now equatorial and vice versa.
So interesting.
Turns out geometry in 3 dimensions is kind of tricky.
Well, it's so strange how they just move. Like even just these
Yeah.
models, you know what I mean?
Yeah.
They just do it.
So
I was like, I don't want you to move, hold still, you little, doesn't work. They know what they're supposed to do.
and so Taylor, look at where the bromine is axial, right?
Right.
When I flip this up, it's now equatorial.
And it stays that
And
way.
it stays that way until it goes through another chair flip.
Right,
It can-
'cause even though the next step of the chair flip changes other things, it doesn't change that.
It doesn't change that one, exactly. And so it's actually kind of satisfying to actually have the model because you can actually see it instead of just having to purely visualize it and doing it on the board. As long as you know how to take it from that and put it on your paper.
Right.
That's the trick.
It's the easy part.
Alright, so why does it matter? Axial versus equatorial? I've already laid the groundwork for that, right? It's the sterics. When things are axial,
Yeah, we've talked about it.
so you can leave it just as a bromine. Just know that your bromine is a methyl group. Or pull it off and put a methyl group on instead, since this could be our next,
Since we made one.
since we made one.
Sterics are the clouds of electrons that push on others. The bigger you closer, the more they push.
Exactly. So if we're in our chair conformation,
Wait, are we?
sorry, just look at the other side for now. Say we're in chair conformation. Our axial hydrogens are all pointed in the same direction, right? Makes sense that they would kind of push on each other a little bit, but hydrogens are small. When you replace a hydrogen with a methyl, all of a sudden, it becomes really obvious that whatever that bigger object is gonna push on those other two positions. They call that 1,3 diaxial interactions. Because if this is carbon 1, the other hydrogens that are axial pointed the same direction are gonna be on carbon 3. You can also just call it diaxial interactions because it's when you have two things that are axial and they're 2 carbons away from each other. They're going to interact and push on each other. And we can see this, we can actually observe this by looking at the different conformers. If we actually take an NMR or an electron microscope picture of these, we can actually calculate, or we can actually figure out that out of these two conformers, where the methyl is in the axial position versus the methyl in the equatorial position, the equatorial position is favored 19-1. So these arrows are equilibrium arrows. When we want to show the equilibrium favors one side really strongly, we just draw that arrow bigger. So it's still just an equilibrium arrow.
Why does it favor it like that? Oh, because then the sterics don't push on each other.
Exactly, because take your model and do a chair flip. Start with the methyl in the axial position. And then if you do a chair flip so that it goes into the equatorial position,
It's out there.
it's out there away from everybody else.
This is a nice big headrest though.
It's a nice big headrest. It's getting in the way of your armrest though. It's so in general, if you've got something attached to a cyclohexane, the largest groups are going to want to be equatorial.
When you have it at your footrest, is this hydrogen not part of the 3 that point down? Like,
It's not, especially because it can rotate.
But then you can be.
but then isn't the up one part of the ones that point up?
The hydrogen that's, it is a little bit, but it's far enough away. And it's a hydrogen interacting with other hydrogens as opposed to a methyl interacting with the other hydrogens. Just, I mean, physically look at how much space there is here versus doing the chair flip and getting how cramped that is. And you can see that that's going to scale too, right? Since I have a T-butyl group built, look how cramped that is compared to doing a chair flip.
A lot going on.
And then you keep
In the beginning.
your largest group. Your largest groups are always going to be equatorial in the most stable state. Because that keeps them away from everything else. That keeps them from crunching into everything else.
Always, you said? I'm saying.
I'm now hedging on that because you know I don't like that
I'm
one.
saying always going to be more stable.
And
Which still might
there
not
could be
100% true, but-
other things happening. If you have two medium-sized groups that, because this is still just looking at one thing attached. As soon as we look at di-substituted cyclohexanes, or tri-substituted cyclohexanes.
So let's look at those after the midterm.
When you, if you were to replace like this one instead of like this one, would it break bonds and switch over to be
No, it would just
more
change
stable?
where the
No.
heads, it would just change.
So because that would be making a different isomer, that's a chemical reaction. All of this, the chair flips, is not actually a reaction because it's still the same molecule. It's just which conformer is it in?
Okay, so if it's like this, right?
Well, you're missing one.
Well, I just don't have any of the hydrogen.
Yeah,
But if it's like this, well, I guess,
that's vote conformation.
yeah, this isn't a chair.
Right.
So if it's like that. If this.
So
is
one is axial and one's equatorial there, right?
That's because you have two groups and you're getting way
Yeah.
ahead of us.
No, that's exactly where we're going next.
Oh, thank you.
So then. They would never both be equatorial or both be axial.
So
if
the
they're right
bigger
next to
one
each
would
other.
be equatorial.
So depending on how they're. What isomer you have. So,
The bigger one wants to be equatorial though, right? So there's less push. Steric
Should be like that, less sterics.
so that exactly. So in that case. You have it set up so that one of them has to be axial and one of them has to be equatorial, right? So you're gonna favor the one that puts the bigger group equatorial. You can have cases where they can both be axial or both be equatorial. So if you look at this example, because of the isomer that it is, they're either both equatorial, or if I do the chair flip, they're both axial.
But it's
Right.
more stable, it prefers the equatorial.
The bigger groups are going to prefer being equatorial.
But that also means it has less energy.
Exactly. That's a good thing, though.
You don't need it exploding.
It's like.
You don't need it
we
exploding
Don't want a
on us.
kid on a sugar high. We want a kid that's very boring and done with energy and wants to go to bed.
Right, where are we going? Let's try.
To bed. We want it to go to sleep.
Things naturally progress towards more stable states in our universe. That's just a fundamental rule of how our universe works, one of the laws of thermodynamics. You wind up getting a chemistry degree, you'll spend a lot of time in P-Chem talking about laws of thermodynamics. And it's kind of one of those, like, this is, that you can imagine a universe where it wasn't the case, but our universe has this rule.
Right.
Energy tends to be minimized.
I don't think either of us would be competitive.
You never know. You might decide to take P-Chem just for fun.
I don't think so.
Maybe you will.
So, and if we replace, I did that example where I replaced the methyl group with a T-butyl group. And it goes from being 95% favored.
Sorry, just
Yeah.
realized that.
If you use the chicken foot one, the T-butyl group, it's 10,000 to 1.
But
It favors keeping it in the equatorial position. The bigger your group, the bigger this split is, right? Because the more those diaxial interactions are gonna throw things off. Right, so there's a table. We love tables.
Should we know this table by heart?
No.
Okay.
It's useful mostly in terms of being able to estimate how big the different substituents are. So if you replace a hydrogen with a chlorine, kind of what we started with, we said it was bromine, but if it was chlorine, it's only a 70-30 ratio. It favors having the chlorine in the equatorial position, but it's not that big of a deal. Because chlorine is just not that large. Oxygen favors F being equatorial a little bit more. Methyl even more so.
Are there numbers on this?
But chlorine is gonna be one of the Mount Rushmores that's electronegative,
It is, but it's not that big. It's not large physically.
but it's not gonna, so it wouldn't affect the energy because of that.
Right. So it's not gonna affect the sterics.
Sterics.
It'll affect,
Yeah,
the charge distribution,
yes.
how polar the molecule is, but it's not gonna affect the sterics because it's not that much larger than a hydrogen, honestly.
Right.
So, and then, but you can see as we get larger and larger, a methyl group versus an ethyl group is actually a really small difference. Turns out an ethyl group is not all that different in size, mainly because the other carbon can basically rotate out of the way. You picture putting the other carbon on here. This second carbon is not really gonna affect the 1,3 diaxial interactions very much because it's just kind of out here past everything else.
Yeah.
But when you replace all three of the hydrogens with more carbons, like for this group, for the chicken foot, that's huge now, because now it can't rotate out of the way, because every time it rotates out of the way, another methyl group comes in and takes its spot.
But can't it kind of be staggered a little bit?
A little, but it's still huge compared to
Yeah.
these other groups. And so a methyl group versus an ethyl group versus an isopropyl group, they're all relatively close to the same size because they still have one hydrogen that can rotate over and take up that space. As soon as you make it, so the isopropyl group, the methyl ethyl group. So there's a methyl ethyl group, right? Let me put it in the axial position.
Oh, yes.
So
It's not, it's methyl ethyl.
here's the ethyl with a methyl attached. I think you're both saying the same thing. So even though it's a methyl ethyl group, it's a big isopropyl group, it seems like, but it has one side of it that's not that big.
So it can rotate nicely.
So it can rotate nicely. As soon as you add that third methyl on there, now it doesn't matter which way it rotates, it's getting in its own
And
way.
that's the second to last one is a
That's-
methyl ethyl?
Correct. So there's your methyl ethyl. Still favors, it's not that different than just a regular methyl group. But as soon as you put that third one on there, or as soon as you go from being a chlorine to being something like an iodine, iodine's huge. Iodine's almost as big as a methyl, as a T-butyl group.
This whole thing?
Yeah. So iodine's in the fourth row of the periodic table now. So we're talking about N equals 4 energy level, takes up a lot more physical space.
Right?
T-butyl's the chicken foot. T-butyl,
Also,
Isopropyl.
we're both missing dark blue, bromine.
oh, so am I. I've just been using the purple for
Oh,
bromine.
you have dark blue.
Oh, you suppose I do. It's a good thing we don't need it that much,
Is that what?
because all the halogens, we just they kind of get used interchangeably.
Those are V bonds for space filling models.
Hang on, but if we wanted to say like this whole thing
Is one iodine.
is one iodine,
Sure, you can do that to represent it.
it's space difference.
Absolutely.
But that's still too little.
Well, but it's better.
It's
I need
better.
a big ball.
Well, and actually, I am just going off of memory. I know bromine's big. I don't know if iodine is as big as a T-butyl group. It's gonna be
It's bigger than bromine.
bigger than bromine. It's gonna be bigger than the rest of these. I don't know out of these which one it's gonna be larger, but
When you say that it's bigger, is it just the bromine itself or the iodine itself or like the whole steric cloud?
Yes,
Both. All.
Okay.
because you don't have the iodine without the steric
Right.
cloud around it. So that's kind of part of the iodine. All right, so if we have two things attached to a ring structure. So I'm just gonna say we're looking at dimethyl now. If we have dimethyl. It's gonna change a little bit. Depending on which way those methyls are attached. Are they on the same side of the ring?
But they can be resonance structures.
No, because resonance structures only involve moving pi bonds. We're not even touching pi bonds yet. But luckily, pi bonds don't affect this very much. So we probably won't until much later. Right. What does change though is that this molecule is not the same as if they switch sides. So if I force it to be flat, which we know is not the way that it's actually going to be. Having them on the same side of the ring, like picture the ring, if the ring is flat, they're either both above the ring or one can be below the ring and one above the ring, right? And just doing a chair flip doesn't affect that. It can be one axial versus one equatorial can change. But they're either both above the ring or both below the ring. So if we were drawing it flat,
But you can't have one.
Axial and one equatorial?
you can. But you can't. So if we had this structure, they're both on the same side of the ring, right?
Yeah. Adjust.
So that's what I drew here, right? Or what I built here.
Yeah.
If I now put that into its chair configuration, we get that one's axial and one's equatorial. And if we do a chair flip, all the axials and equatorials flip, so we're still gonna get one axial, one equatorial.
And the axial one is not the one on the footrest.
The axial one is this one, yeah.
Yeah.
Equatorial points away from everything else, axial is the one that flips up and down.
So if you always add it to the footrest, it's always gonna be equatorial.
No, because you can put it on the footrest. It's equatorial now, but if I do a chair flip,
Well, when it's in the footrest position. Whatever is added to the footrest in footrest position is gonna be equatorial.
well, so watch this. And we just change which was the headrest and which one was the footrest.
Now it's going down.
And now it's axial. So just flipping it around and rotating it is not gonna change whether it's axial or equatorial, but it can change whether it's the headrest or the footrest.
Still not convinced this is what makes up everything in our lives.
Not yet.
I know, I'm like,
Even these little balls, that's all that's going on inside.
I know, I'm like, these are making up these.
Mind blowing, isn't it?
It's so weird. I try to explain it to like, I like have a hard lecture and I'll be like, it was so hard. And I try to explain it and he looks at me like I'm insane.
So
Gets even weirder when you think about not only are hydrogen atoms and carbon atoms making up our models of hydrogen atoms or carbon atoms. They're only models of carbon atoms and hydrogen atoms because we choose to view them as carbon atoms and hydrogen atoms.
Shush,
Don't-
shush.
We bring consciousness into it and it gets really weird.
Okay.
I don't want to think that they're anything else. They are carbon.
That's
and
like, did
hydrogen.
you, oh my goodness, did you hear about the new quantum, like, time stuff that's coming out? Where
What?
future events are affecting past events? So like people are explaining gut feelings now as like something has already happened that made you feel that way.
It could conceivably be the case. There's also the theory that there's only one electron in the universe, but it's not bound by time. So all the different electrons are all the same electron
like it.
interfering with itself by traveling back in
So
time.
we are all the same electron.
I don't like
In
it.
theory.
I don't like it.
That is, the math works for that.
No,
But you have to make some other assumptions and there's other ways that the math works better, in my opinion.
So
But
like
it's not, we can't
Optim's-
rule it out yet.
The Optim's razor or whatever, time is a
but
big
I just touched
assumption.
her.
It's true. It's true.
No, well, no, we're technically not touching, it's just our
But I can
atoms pushing on
feel
each other.
you.
It's the atoms pushing on each other, Taylor. None of this is real.
Alright, so here's our other way of thinking about, so axial and equatorial, we're getting the hang of,
Yes, kind of.
kind of. So now we're gonna talk about cis versus trans, and these are isomers, not conformers.
Okay.
It means you can't switch back and forth between them without actually breaking bonds. So doing a chair flip is not making different isomers, because we didn't break any bonds to do it.
So an isomer, you have to break a bond to do it.
To switch from one isomer to another, you have to break a bond.
Did you do a resonance structure?
No. So resonance structure, yes, but no. Resonance structures, one of our rules was we don't break any sigma bonds. We don't break any of the strong bonds that hold it in place. So different resonance structures are never gonna be different isomers from each other. Because an isomer, you have to break a sigma bond. I should have been more specific.
But what's? How are the definitions different? I'm still a little.
So
So-
conformer would just be how.
Conformer is written differently.
Conformer means that it's the same molecule written differently, yes.
Isomer is.
Means it's a different
Different
molecule.
molecule, so then.
Our,
yes.
our dividing line between the two is, do you have to break a sigma bond?
Okay, so resonance structures are just. Conformer, what's the first one we talked about, isomer?
They're like a special version of conformers. It's like an electron conformer. Is a resonance structure. Resonance structures only involve moving electrons. Conformers involve moving the nuclei.
I say conformer instead of conformer.
Conformer.
Does that make you know what it is? Cause we've definitely said that.
Isn't the conformer just a different written structure?
Yes. So now we're saying, we can't just say, oh, they're bouncing around. This one went peace out and then over
He
here.
isolated himself.
That's it. That's an ice, exactly. You can think of it that way. Use that root.
So we're done, broke up.
So,
Divorce.
so far we've dealt with isomers where we said, okay, well, 2-methylpentane versus 3-methylpentane. Those are two different isomers.
Yes.
This is another type where it's not 2 versus 3. In both cases, you have methyl group on carbon 1, methyl group on carbon 2. But if they're on the same side of the ring versus opposite sides of the ring, because the ring can't rotate freely anymore. And so we call that cis-trans isomerism.
So is there a difference between cis and trans isomers, or is it
Yeah.
all one?
Yeah, look, the
Yeah.
bigger groups are both on top, or they're not.
Okay, wait, I need.
Yeah.
Cis.
Cis is straight, right?
Cis literally means same.
Well, like cis white male is a straight white male. Cis is straight.
No, it's a male who hasn't changed his gender.
That, whatever, it's straight.
Sure. So,
Leave the straight term out of it because cis and trans in terms of gender comes from this.
right, because cis is same.
Cis means same, as in same as what you were assigned at birth.
It's that same for a second.
Same.
But then trans. would
Trans
be-
means you've gone
switched it.
The original root of the word trans means across. It's like the Trans-American Railroad, you remember learning about that in high school? It's called the Trans-American Railroad because it went from one side to the other side, it crossed America.
Let's tell you it changed his gender. Okay, so.
Okay, wait, so
Don't
it's
get into that too much at this point.
cross.
So trans means across,
And same.
cis means on the same side. So this molecule even though one is axial and one's equatorial, that's not what we're talking about. It's still cis, because if I flatten it out, they both stick up above the ring. And some axial or some
Can it be trans
positions,
on the same one?
no, because then it's symmetrical.
Oh, then it's just cis this way if you look at it a different direction.
Right. So this one's cis, if we flip it like a pancake, it's cis with both of them down.
Achiral.
Symmetrical is achiral, very good. See, it's coming.
I just have to like say it a million times while we're going through other things to connect all the things.
The chiral stuff is over.
Right, we're gonna do another, half lecture of that on Tuesday, spending more time on chiral versus achiral as well.
And then you said lab Tuesday was review.
And lab Tuesday will be review.
This is trans.
That is trans. And as it's drawn, they're both axial.
Yeah. Could they, one be axial, one be chiral?
Axial versus equatorial.
That. What's chiral? Where did that come from?
That's the four
Oh.
different, or
4 different things attached. That's a different thing. So right now, it's cis and one's axial and one's equatorial. If I move it over,
is this possible?
Or did I just-
those things,
The way it's like overlapping.
Yeah, those are the Newman conformers that we've been drawing.
It is kind of, yeah, a little bit.
Conformers, was that the right word? Newman
Uh,
projections?
Oh, so this
Projections.
would be one and this would be a second one?
yeah, yes.
Okay, it's coming together.
You just over exaggerated the angles so that you could see things better. And that's normal. That's fine.
So it's this one?
Yeah, but with a methyl. Cause then the hydrogens are,
Well, so I guess what's incorrect about this is that by do it like that, just so that you're not pointing this one actually into the ring.
okay.
But yes, then that small
'Cause that's
adjustment,
that same like.
yeah,
diamond
exactly.
shape.
And that is exactly why equatorial is more stable, because you don't see this big methyl getting in the way of everything else as much. You do the chair flip with that. They're both equatorial right now, right? Do the chair flip.
I'm struggling.
Mostly
I was almost there.
like that.
Okay,
Now, look at it that way.
yeah,
And now, and actually, there we go.
so those.
Those ones are
This is interacting with these two,
Okay.
and this one's interacting with these two.
oh, it's one of your feet.
What? We have 3 feet on our chair.
Yeah.
I
Alright, so,
hate the idea of divorce over breakup, because I think we talk about resonance structures as breakups, right?
they're a little more fluid.
Yeah,
Divorce is a lot more
Always
final.
Get back together.
yeah, they're playing around. They're playing the field, that's what it's called, right?
I don't know.
Alright, so. To finish this thought. Cis, this is basically just gonna be a new thing we add on to the front of our names, a new prefix.
Or
Yeah,
How long do these?
I have no more space on my prefixes naming card.
Well, you better make another one.
yep. So cis, if they're on the same side like this. This is a cis isomer, so we're gonna say, okay, what's cyclohexanes, the parent molecule still? It's 1,3-dimethyl cyclohexane. And they're on the same side of the ring. So it's cis 1,3-dimethyl cyclohexane.
Okay.
If it was on the opposite sides, we would just throw trans in front of it.
It's gonna be on the quiz, isn't it?
Yep.
Yep.
And axial versus equatorial.
And chiral and achiral.
No, we'll spend more time with that on Tuesday. I want you to be aware of that concept. Because we're starting to think in 3 dimensions.
Well, why does that matter?
Chiral versus achiral. Because it turns out the binding sites in enzymes are chiral.
So you need chiral molecules.
So different chiral molecules will bind to different binding sites.
But
Circle
achiral,
this whole time.
I think achiral cannot bond to your enzymes.
So depends on what the enzyme is. But think of it like the model that they use in biochem is a lock and key. A key to your door is chiral. If you took a mirror image of your key, it wouldn't fit.
Right.
Right, so it's not just that the active site is a circle, it's a lock.
It's a
And-
sphere.
Or you can think of it as a glove that a hand is trying to fit in.
So when they make something like a flu shot, everything in that flu shot has to be chiral?
You have to pay attention to it in certain cases. Vaccines are a little bit different because we use live cultures to make them, and so there's a lot of everything in there.
When they change the flu vaccine every year to say this is the projected
Right.
strain of
Yes,
flu.
yes.
But for DNA is chiral. DNA rotates
Not
clockwise, not counterclockwise, because it's made up of chiral molecules.
So the mirror is not identical.
So the mirror is not identical, and our proteins are made up of chiral amino acids. If you tried to make the same protein out of the opposite mirror image, you'd get a mirror image protein, which may or may not fit with the rest of the molecule or the rest of the cell, what the cell needs, because maybe it doesn't bind to collagen as well, because it's the reverse instead of being, so you can't fit the collagen key into the enzyme active site because you took a mirror image of the enzyme active site.
Why'd you do that?
You wouldn't. But that's why it matters, is because,
Like,
so-
dumbass did that.
so this is a good example of why chirality matters. There was a medication that got prescribed mostly in Europe in the 60s, called thalidomide. It caused birth
Yeah,
defects.
the show that was in it.
I think
Yeah.
I've heard about this one.
So, and it's because they didn't understand how chirality could matter at the time, because it was the 60s, they didn't understand biochem as well. And it was a lot easier to make thalidomide in an even mixture of the right-handed and left-handed version. The process that they had made even numbers. So rather than separate them out, they just said they prescribed it as a mixture. One of the mixtures worked really well as an anti-nausea drug. The other one stops cell growth.
So
That's
And
why
they were
they-
prescribing it for morning sickness.
Yeah.
the tablet.
Yeah, so the tablet was both the right-handed and the left-handed.
They fixed it. Is it called something else now, or is it still?
It's now so tainted, the name is so tainted that they can't use it. They're actually using the version that stops cell growth as an anti-cancer drug
I
now.
was gonna say,
So now that we understand why it did that, but they're not prescribing it as an anti-nausea anymore because it's
Does it do it?
canceled, to use that term. What's that? Yeah, it's really good as an anti-nausea drug.
That stops cell growth.
No, that one doesn't do any of that. So they were prescribing two drugs that were the same molecule, but one right-handed and one left-handed.
But then not every woman taking it had birth defects.
No, they pretty much did. If they were pregnant when they were taking it, it caused
Yeah,
terrible, like missing limbs,
yeah.
missing organs.
also an example of why we can't just pancake them anymore at this level, right?
Right, why we can't just pancake, and that's also an example of why our Food and Drug Administration in the United States, the US did not have this problem. Because our Food and Drug Administration takes longer to approve things on purpose. Part of its function is to be slow. So that we don't do dumb stuff in the name of capitalism.
See other people do it wrong.
And we can see, it provided a lot of. And basically there was push from the pharmaceutical companies to approve it in the US. And the FDA tried to approve it, but there was one woman who worked at the FDA who said, no, we're still waiting on these trials. You can't prescribe it yet because we're not gonna rush it because this is our process. And because she did that, there was 9 months of not having those horrible birth defects in the US that they did have in Europe. So win for women, win for bureaucracy. I don't say that often. And that's why we have to pay attention to it at the OChem levels, because it's gonna inform our understanding of it at the biochem level and understand why it matters at the organism level.
Interesting, cause I watched a show, a midwife show
Mhm.
of like the 50s, 60s, might even go to the 70s and 80s now, in the UK area. And like
Yeah.
all, in like one whole season is all about like the controversy of some of these kids being like born with these defects from this medication that I didn't understand why.
That's exactly, they were prescribing two
Yeah.
drugs at the same time without realizing
So
it.
at that point, did they not know about right-handed versus left-handed?
They didn't understand the biochemistry of the active sites.
So then that taught them a lot more.
It gets used as a cautionary tale, and anytime they start thinking, maybe we should streamline the drug approval process,
They're like, maybe we shouldn't.
maybe we pump the brakes on that a little bit.
Yeah.
But yeah, we did learn a lot from that. It's hard to understand. It's a little bit like AI is now. Biochemistry in the 60s didn't even exist as a field of study. You couldn't get a master's in biochemistry or a bachelor's in biochemistry. You got a bachelor's in chemistry with an emphasis on biology.
Right.
And Isaac Asimov, who wrote I, Robot, really
Oh, yeah.
famous sci-fi author.
Yeah.
He actually was a PhD. He was a full professor at Columbia in biochemistry before biochemistry was a department.
Interesting.
One of the most prolific authors of all time. He wrote textbooks, he wrote articles, he wrote like popular science books.
Yeah.
But yeah, they were learning new things every day in the 50s and
Right.
60s when it came to biochem. But they were also figuring out how to make new drugs every day. And they didn't always
Know the science.
go at the same rate. We still do that. We still don't understand why SSRIs work the way they do.
What are SSRIs?
Antidepressant. So Prozac is selective serotonin reuptake inhibitor.
Use trazodone as an antidepressant.
They were like, just go to sleep.
now. Yeah,
That's so
and like the
funny.
dose of trazodone I want to help me sleep is like 50 milligrams, and I like fourth my tablet. I can't get it in any less. She's like, yeah, they would give you like 400 milligrams, and I'm like, 15 milligrams knocks my ass out. What do you mean they were giving 400 milligrams?
You're like, these people, they just need some extra sleep.
It's
That's insane.
it is, and there are some really interesting stories about drug discovery as well. Like Thorazine. Thorazine's an antipsychotic.
Okay.
So it gets basically what they would give somebody who is having a schizophrenic attack in they would inject them with Thorazine to settle their brain down. They only discovered that because somebody realized that it dropped the body temperature and slowed the heart rate.
That seems dangerous.
Why
It
did they learn
does.
that? How?
So because the treatment for schizophrenic attack before Thorazine was to wrap the patient in a wet blanket. Literally, that's
Did
where
it
the term
work?
a wet blanket comes from.
Did it work?
Yeah, but it lowers the core temperature and it slows the heart rate.
Imagine trying to put that on someone having a schizo episode though. You're like, come here, let me hug you.
Why we don't do that anymore, why we can inject Thorazine instead, and it has the same effect on their core
Yeah.
temperature and on their heart rate.
Yeah.
But they only figured that out because somebody's like, well, it does the same physiological
Right.
thing. What if we tried using this medication instead? It certainly is. All right, so quiz this weekend,
Yes.
a little bit of practice, system trans.
Okay.
We're not gonna get into chirality today, but, and then I'll probably do build a model. Which is the more stable, draw both versions of it,
You want a picture of our building?
No, we gotta draw it.
or I would like you to practice drawing it.
Right.
And
But
take a
like,
picture of the
you
drawing.
want us to like take a picture of our model as well to make sure.
If you
we're
wanted
drawing
to,
it
if you wanted to
correctly?
do that, I will look at that to make sure that you built your molecule properly and translated it properly as a way of showing
Yeah.
your work. Sure.
Exactly, like how like people are like, okay, show me all your work, even what you plugged into your calculator, and like, if you plugged it in wrong, but you're doing the right thing, you can still get like partial.
Yeah. Yes, you can include two uploads on that one. One as your paper product or paper final answer and your, here's my model. And then we'll talk about chirality and reactions on Tuesday. And then we'll be set. If we don't get through absolutely everything, then I'll amend the test a little bit
Okay, before Wednesday.
before Wednesday. I won't give it to them till I know what we get through on
Okay.
Tuesday. Because
Yeah, right,
I wouldn't do that to you.
Like, we learned nothing on that.
I always felt so bad, like in biology, she would add extra credit questions, but we'd be like in the classroom when she would tell us stuff, and so I'd have to be like, so you gotta go let SAS know.
I'm glad that someone was vouching for